It's kind of odd being at MathWorks event and not talking about MATLAB, but today I'm going to be talking about robotics. I think we're all a bit conflicted about robots. We don't know whether we should love them or whether we should fear them. Right? We don't know whether they're here for us or whether they're going to be against us. As a roboticist, I think my big worry is that we just can't make them competent and reliable. But I think this is just a temporary phase that we're going through. And over the coming years and decades, robots are just going to get more and more powerful, more and more capable. So yeah, there are some issues, I think, about the risks of robotic technology. It's a topic that a few people are starting to focus on. I think probably as a society, we should be starting to have these sorts of conversations already. As a roboticist, I guess we're driven by beacons on the hill, robots that are intelligent, that are capable, that are competent, that are useful. And we strive to build machines like that. And we're way, way away from being able to do this at the moment. So, you know, the images that Hollywood dishes up to us regularly of machines that are perhaps annoying, but certainly very smart. R2-D2 is less annoying. You know, he's kind of a superb engineer, can hack a Death Star, fix an X-wing fighter. These are the sorts of things that we aspire to. The sad reality is that these robots that you see, that you're impressed with, aren't robots, right? They're people dressed up as robots. And even in the most recent Star Wars movie, the BB-8 robot, right? It's a puppet in a lot of scenes, or it's a remotely controlled machine. It's not a robot. We can't build robots like the ones I showed you before I kind of disappointed you by showing you what the reality is. So the reality of robots today is actually much, much more like this. So this is a Tesla line, I guess not too far from here, somewhere in California, and it's building cars. This technology is really almost 60 years old now, since the first industrial robot went into service. These robots are really fast. They're incredibly accurate. They can carry very big loads. They don't get tired. They work 24/7. And here you see the human beings are almost the servants of the robots. They're delivering parts to the robot, and the robot is the one that does the assembly, because they can lift these big pieces without hurting their backs. And they can do it very precisely. They can do it indefinitely. These industrial robots are actually quite dangerous machines, and they're dangerous because they can't perceive the world that's around them. All that they know is they measure the angles of their joints with encoders, and from that they can figure out where the tool is, and they use a control system to simply move the tool from one point to another. They have no idea what's going on around them. If the object that they wanted to grasp wasn't there, they'd close their gripper and just move anyway. Right? So they're very, very dangerous. They can't see people around them. So we put them in cages, we put them behind optical barriers in order to keep them safe. So there's this big dichotomy between the robots that we dream of on the right and the robots that we actually have today on the left. But the ones on the left seem a little disappointing in comparison to the one on the right. But the ones on the left are doing a useful task, right? They improve the productivity of the factories. You know, they make money for their owners. So, you know, it's been a very important technology, a very valuable technology. But what we're going to see in the future is that the kind of jobs that these robots do is going to get more and more diverse. They're going to move out of the factories, and we're starting to see that now with robot vacuum cleaners and self-driving cars, and there will be more and more examples of that. And I'm going to talk about some of those examples today. I mentioned that the robots that we have now, the manufacturing robots, are dangerous things, and we put them in cages. I guess the big breakthrough in recent years are robots that we can work near. So on the left-hand side, we have Baxter, a human-safe robot made by Rethink Robotics, a Boston-based company. And here you see it very laboriously attempting to fold a shirt. Watch the video for long enough, yes, it will fold a shirt. But Baxter has got a vision sensors in his head, and he's got all kinds of force sensors in his arms and his wrists. So if you were to insert yourself in his workspace, and if he touched you, he would stop. He wouldn't hurt you at all. The robot that you see on the right-hand side is the Hubo robot. It's the one that won the DARPA Robotics Challenge last year. Came out of KAIST in South Korea. And he's a tele-robot. So he has some innate autonomous capabilities, like to pick up an object, to walk forward without falling over, is done autonomously, locally, using control loops on board the robot. But a lot of the planning is actually done by people in the back room. They're looking at the camera feeds and the point cloud feeds coming out of the robot, and they're planning what to do next. right? So it's a mixture of teleoperation and full autonomy. So, you know, Hubo's probably a good example of a sort of state-of-the-art humanoid robot. But you know, in this case, you see that sometimes he crouches and sort of drives along on his knees, which turned out to be a much more reliable mode of getting around. Almost all of the full humanoids in the DARPA Robotics Challenge fell over at some point. So humanoid robotics has still got a lot of room to improve. Thanks, Corey. Perhaps one of the most successful applications of robotics is Amazon. So I heard a talk by a guy from Amazon a few weeks ago. Amazon own now 30,000 robots, and they are absolutely integral to their business. So what you see here are these robots created by a company called Kiva Systems, which Amazon bought for a large amount of money a few years ago. And these robots scuttle around the floor and they pick up the shelf units and they bring them to the person who's actually fulfilling your order. So when you buy something from Amazon, at the end of the day, you get a cardboard box with your items in it. Items are not filled by someone taking an empty box and walking around the warehouse looking for the things to put in the box. They stand still, and these robots bring the shelf units to the person who's dispatching your order. And that way they can get massive efficiencies, massive productivity, with a relatively small human workforce. Another example of a robot doing, a robotic hand doing some manipulation to show the sorts of skills that we can create in robotic systems. What we don't have really at the moment is a general theory or general way of creating robotic systems. So yes, we've got really good hands and people are working on good vision systems and some people are doing heads and some people are doing legs. What we don't have is all of this goodness in kind of the one low-cost system that you can use and will perform some sort of useful task. This is another example of robotic technology. This is an exoskeleton, commercial exoskeleton, and I filmed this at a robotics show a couple of years ago. So the guy on the left-hand side is wearing an exoskeleton. It's carrying a lot of the weight. It's not his musculoskeletal system is not carrying the weight. It's the external mechanical skeleton that's doing that. And so his mate's going to keep loading him up with stuff, and he's going to be able to carry that quite effortlessly. And the exoskeleton is a robot, but its motion is not programmed. It's a control system that's trying to follow the wearer. So the person moves this way, the exoskeleton moves that way. So it's a very kind of close dance between the exoskeleton and the wearer. This is a movie from a long time ago, 1966, I think, called Fantastic Voyage, where they're trying to fix a person by miniaturizing a bunch of people in a little spacecraft and injecting it inside somebody's body. And that's been a big problem for surgery for a long time. In order to fix something inside your body, you need to make a hole in the person's body that's big enough for the hands to go in to do the manipulation. And that's actually got quite adverse outcomes for patients. So we do this today virtually. We virtually put the surgeon inside the person's body. So there's the surgeon sitting over there, and he's looking at imagery through the screen here that's coming from cameras inserted through one hole in the abdomen. He's manipulating little haptic joysticks, and they're moving little tiny tools inside the body. So the surgeon actually feels immersed. It feels like he's inside the patient's body, but he's not. And it's a very, very effective way of doing surgery for both the patient and for the surgeon. So lots of people ask me, what's the definition of a robot? And the simplest definition I have of a robot is it's a machine that moves stuff from A to B reliably, consistently. It might move big things from A to B. In this case, it's moving pallets around a warehouse. It might move very big things from A to B, and they might be containers in a container port. An autonomous car fits that kind of model as well. So really quick introduction to some of the things that robots are and some of the things that robots are not. But if you look at a lot of industries, they don't have the penetration of robots in these sorts of industries, which are economically very, very important, is almost minimal. Building and construction, massive industry in most developed countries. Very, very little robotics indeed. Agriculture, not much robotics. Healthcare, not much robotics. A lot of manufacturing, still a lot of manual piecework, not much robotics. So as a roboticist, I have to ask the question, why aren't there more robots around? And I think that the reason is what you think of as Moravec's paradox, I think is a nice way to start to think about this. So Moravec's paradox is things that are hard for people are easy for computers. Right? So the example here of the Go game and the chess game nearly 30 years ago, nearly 20 years ago, sorry, are examples of things which is the pinnacle of kind of human intellectual endeavor, the game of Go, the game of chess. And we can put that in a box, we can compute that. That's pretty easy. Conversely, the other part of the Moravec paradox is things that are easy for people are really, really hard for computers or their close cousins, robots. So in this case, this child is able to manipulate a chess piece, might even be able to recognize a knight and pick it up and hold it. This is still a cutting-edge problem in robotics. We would struggle to get a robot, you could say to it, pick up the black knight, and it would do that. Now, we might be able to handcraft a solution to this. We throw enough grad students at it, they could hack and tweak for weeks and weeks, and you have a solution that worked for one chessboard. But lots of different sorts of chessboards. Sometimes the pieces are different shapes, sometimes they're shiny, maybe they're transparent. We would struggle still today to have a robot that had the perceptual ability to recognize the piece that you were talking about and the manual dexterity to pick it up and manipulate it. That's still very, very hard. We can't do that. Another example of a young person. She's trying to solve a Rubik's Cube. She's using her eyes. And this is the thing that robots today do not have. So she's using her eyes to build a mental model, an internal representation of that Rubik's Cube. And then she can reason about that and figure out how it should be changed. And then she's going to manipulate that using wonderful actuators and sensors in her fingers. But she's also going to be using her eyes to control that manipulation as well. So it's a fusion of vision to help her plan what needs to be done, and he's also going to use the vision as part of the execution of that plan. Another example, someone juggling. And here the person's got some internal model of how things move in a gravity field. And they're using muscle memory and this internal model as some sort of feed-forward control, but they're also using their eyes in a feedback control sense to keep the juggling all synchronized. Another example, driving. It's largely a visual task. We're looking at the windscreen and we're using what we see to control the steering wheel and the pedals and to recognize objects and maybe even predict that the pedestrian is going to move into the road and I need to do something different, or watching the other cars and predicting. But the primary input is always visual. So the sense of sight is absolutely our most impressive sense, and I'd argue that robots that don't have the ability to see are profoundly disadvantaged and will always be profoundly disadvantaged. What's really amazing about the sense of sight is that it can tell us about things at a distance. Of all the senses that we have, like we have a sense of taste, and that works not very far away from my body. Sense of smell works a little bit further. My sense of touch works this far, but no further. With my sense of vision, I can see things from here out to the horizon. So it's the ability to see things that are far away is really important. It gives you lead time and ability to plan and react. It is a very, very impressive sense. And unlike LiDARs and sensors like that, it tells us information that's it helps us discriminate objects. It tells us not just the shape, the geometry, it gives us color and texture and things like that, which are really important when it comes to object recognition. So, argument should be, robots should be able to see. And the next part of the talk, I'll give you a couple of examples of robots we've created that can in fact see and use vision in a very active kind of way. And Hollywood's ahead of us. All the robots in Hollywood, they all have eyes, right? So it must be right. So, look at the human visual system. We've got two eyes, two cameras. They're pretty decent cameras, 120 megapixel, 20-bit dynamic range. You could probably buy them from the shop. They're going to be expensive, but that's not beyond our ability. We've got accelerometers and gyroscopes in our head, and they're really important to help us see the world. And that sounds odd, but they help us disambiguate my motion from your motion. If things are moving in my visual field, it could be because I'm moving or you're moving. The motion sensors help us break that ambiguity. And motion sensors are really cheap, right? That's not an issue. This is the kicker. This is where we struggle. The back 1/3 of your brain, about 3 by 10 to the 10 neurons, right, weighs half a kilo, consumes 6 watts, and tells you everything about the world around you. It's astounding. And we're starting to make some progress in being able to mimic some of the visual capabilities we have. Deep learning is brilliant, but we run it on huge computing clusters and GPUs. It's taken a lot more than 6 watts. but we're starting to be able to crack the computation, and maybe we say it's just an architecture thing, and we'll solve that in due course. So that's kind of the introduction to robotics, the techie bit. The last part of the talk, the second part of the talk, I want to just talk about the social implications of robots and why we need robots. What are the problems that they can help us solve? And I'm going to do it in terms of 3 graphs. An audience full of engineers, you're going to get graphs. So I'm going to go through them one by one and connect them to robotics for you. So the first one is population. Population's a problem. Maybe we've got the second derivative of population growth under control. The first derivative is still positive. And the implications of increased number of people on the planet, we're going to need more food, more transportation, more resources. And robotics have a role to play. And given I don't have too much time, I'm just going to concentrate on the food bit. United Nations thinks that by 2050, we're going to have increased food production by 70%. That's a big lift. We need food for people. We need food for animals, which then become food for people. We need food for our cars, which is perhaps one of the stupidest things we ever tried to do. Make a lot of good food from good land, and we put it into automobiles, but we do. We build houses on it for all those extra people to live in. We have room for burying all the dead people. That takes land, and in China at the moment, this is a really big issue. But over time, despite all of those challenges, over time we have increased the amount of food production on the planet. The issue is whether it will continue to go at the rate that it has. Food production in the last 100 and 200 years has been driven by probably 3 revolutions. One in genetics, one in mechanization, so we've moved from people to horses to tractors, and the other one is in the use of chemicals. These are not sustainable, and some of these are already, we've reached our limit. We've done all of this simultaneously reduced the number of people who are involved in food production. So this is a graph from the US. It's plateaued out at a very tiny percentage of your workforce is involved in food production, enabled by those revolutions. Mechanization. It's going to be hard to make machines too much bigger. Make them too much bigger, the chance of them getting stuck in the ground is much, much higher. But there's also this interesting problem is where they drive across the fields, they compress the soil and damage the root structure. And so the one solution to that is to have GPS-guided tractors which just go up and down and destroy just the same bit of ground over and over again. But still, you can argue they're taking about between 3–4% of arable land is being crushed to death by big agricultural machines. It's a waste. Another issue is weeds are fighting back. Just like bugs and antibiotics, plants over 50 years that we've been pouring herbicide on them, some of the weeds have become resistant to the herbicides that we use. And that's a problem because there aren't any other herbicides that we can apply to these weeds that are not incredibly toxic and we don't want to get out into the world. So that's a really big problem, and this number of resistant species is growing all around the world. Farmers are getting older, particularly in my country. Young people are not aspiring to become farmers, so that's a problem. So we created this machine. We call it AGBot 2. It's the second generation of agricultural robot that we created. It's an electrically powered vehicle. It looks at the ground that it's driving over, and it classifies in real time using deep learning techniques the particular sort of plants that are there. So it can detect a wild oat, which is not a good plant. It can detect a cotton plant, which is a good plant, sow thistle, whatever. So we can classify the plants that the robot's driving over, and then we can apply the appropriate method of terminating the plants that we don't like. So we'll get to that in a minute. So here's the robot trundling over the ground. Here it's applying herbicide. It's only applying herbicide to the weeds, where the weeds are, and to the plants that it doesn't like, that it's classified as a weed. This can reduce the amount of herbicide that's being applied by maybe 90%. And the plants that are resistant to herbicide, we can chip them out of the ground using this controlled mechanical hoe. So it's going to take a long time for plants to become resistant to being hit by a bit of metal and dragged out of the ground. Or at least that's our hope. So in some ways, what we do with a robot like this is like going back to what we used to do. We've had maybe half a century of industrial agriculture where we treated every single plant the same. We didn't used to do this, but it was convenient to do that, but it's actually beginning to bite us now. And with robots, we can go back to individually tending to each particular plant because the labor that a robot provides is really low cost. We couldn't do that if we had to pay human beings to do it, but we can do it if we buy robots and get the robots to do that work, particularly in high labor cost countries like the US, Australia, Europe. So kind of like a back to the future thing. This is another robot we created, and this is to do fruit picking. And what he's doing is looking for what I'd call a capsicum, and you probably call a bell pepper. And you can see it there. It's got an Intel RealSense sensor. It's an RGBD camera. It's moving around. It's building a three-dimensional model of what's there. It can segment the fruit based on its shape, texture, and color. And here you see a point cloud representation of the fruit. We can fit a superellipsoid to the fruit. We can plan a point at which we should grasp it, and we grasp it using a suction gripper. We use a little mechanical saw to cut the stem, and then we put it in a tote. This is at the moment way slower than a human being, but we've just finished some recent trials, and we're probably now maybe a factor of 2 to 3 slower than a human being. In my country, we struggle to get people who are willing to do this kind of work. So a lot of fruit gets wasted, gets left on the vine because there isn't the labor available when and where it's needed. If you grow fruit, you've got a pretty small window in which to get it off the vine. This is speeded up. This is times 4. So it actually looks impressive. It's our goal is to make it really that much faster. So it's another example of a robot that can see. We're actually using in real time information from visual sensors and using it to control the motion of the machine to do a useful task. Very, very different to the factory automation task, where in a factory you've arranged all the items you're interested in to be at known locations. With natural product like fruit, you can't do that. The middle graph, an interesting one. It's called the dependency ratio. And this comes back to sort of population dynamics and demographics. And it's the ratio of the people who need to be supported, the young ones and the old ones, the ones who need to be helped, divided by the people who are doing productive work, people in the prime of their life. And this is the ratio. This is computed for Australia, but I think for the US it wouldn't be too much different. And it's quite an interesting shape. So let's go through that. That peak you see there was the baby boom. So post-war, all these people were born. And they all went into the numerator. So they made this dependency ratio bigger. Big is bad. They actually want the dependency ratio to be low. Right? So there's more people to look after the people who need to be looked after. And then all the baby boomers went to work, and they went into the denominator, and the dependency ratio went low, which is good. It's as low as it's ever going to be ever again, I suspect. Because what's happening is the boomers are retiring, and as they move back up into the numerator, the dependency ratio is going to get bad again. And that's a big problem for all countries. These things are called population pyramids, and they show the population versus age in the vertical axis. And if the population pyramid tapers like that, it means you've got a fertility problem. It basically means that every year there are less people being born than the year before. And that's very pronounced in Japan. China, you can see the influence of various political moves on the number of children that people can have. And in India, you can see that they've got a really big problem with healthcare. That people start dying much, much earlier than they do in other countries. So you can compute those dependency ratio things for all sorts of different countries, see all sorts of different dynamics. But what's highlighted there are the people in the prime of their life. So they're the ones who are doing the work, and they've got to support the people above and below that line. Sorry, that's what's left of the baby boom. So as they start moving into retirement, but they're also starting to die out. So it's not much of a bump anymore, not as pronounced as it was back in the day. And this is the healthcare needs of people. And we can see that as they get older, this is post-retirement age, the number of health interventions they need increases. So this is the problem we've got. We've got an aging population. People who are aged need more health interventions. But there are less working-age doctors and nurses to provide that support. So this is the crisis that confronts all countries. Japan is probably ahead, but the rest of us are not very far behind in having to confront this. So a lot of people are starting to think about the implications of this, particularly with respect to healthcare. and you go to a hospital, it's chaos. There's stuff going everywhere. There's people and meals and linen and drugs, specimens. And there's a huge scope for moving stuff around in the hospital. That's what robots are really good at, is moving stuff around. And hospitals are full of stuff, all sorts of stuff being moved around. There'd be huge advantages in automating that. And there's people working on this. So, robotic orderlies to lift people out of beds, machines that carry instruments from one ward to another. Down the bottom right is a fictional depiction of a helper robot. This is in the movie called Robot and Frank. It's a robotic companion and nurse, if you like. And up the top there, robotic surgery that I've already mentioned. Huge scope. Last one I want to talk about, I don't have too much time left, is around the environment. It's monitoring the state of our planet. It's our biggest asset. It's our most important asset. And the laws of asset management, if you want to look after an asset, they are inspect it, and inspect it again. And we inspect our planet in a really sort of ad hoc and primitive way. All sorts of biologists and environmental scientists, marine biologists out there inspecting the planet. Very, very labor intensive. In all these scenes, there are pictures. There's not much automated gathering of this kind of data. We probably do a better job of automated inspection of other planets than we do of our own planet, though it's a significant cost to do that. And yeah, we've learned fantastic things about Mars by sending robots there to do the work that otherwise would be done by people. There are some examples of robots doing environmental monitoring. Perhaps one of the most successful, the Argo floats. Nearly 4,000 devices floating in the oceans that go down 2 kilometers and come up to the surface, measure stuff, send it back by satellite. And they provide foundational information for climate and ocean models. A colleague of mine had robots on lakes measuring the amount of methane emission as a function of time and space. Had colleagues using unmanned aerial vehicles to monitor dugongs, which are marine mammals. But the one that I want to talk about the most is this particular creature. This is called a crown of thorns starfish. It eats the Great Barrier Reef, which is kind of sad. Great Barrier Reef should be pretty colourful, full of nice coral. The starfish go through, it turns it into this. So they're not very popular with people who manage this marine resource in Australia. So some scientists developed a toxin, and divers could go around and they could find a starfish and inject it, and it would eventually kill it. And by that means they can keep the population of these starfish down. The population's gone up because of environmental damage we've done to the reef, increasing sediment, chemicals, pH change, temperature change. So it's not the starfish's fault, it's kind of the innocent victim in all of this. So as roboticists, we thought we could do this. We don't need divers. So we built this machine last year. We call it COTSpot. COTS being crown of thorns starfish. It has a deep inference system on board. So the first step was to gather data, collect images and label them of crown of thorns starfish. Don't find many of these on Flickr. So we had to collect the images ourselves and label them. And once we'd done that, we'd collect many, many thousands of images. It was very tedious. And this is to demonstrate the detection system. So the circles indicate where it's a bit interested, and in a moment you'll see something that it's very interested in. It can very, very reliably detect the starfish. This is the injection system, first trial of injection system. So there's the vehicle and the pneumatically powered arm stabbing some sand, and in a moment you'll see it injecting a starfish. So it works. So we're looking for sponsors at the moment to allow us to build large numbers of these and put them to sea. All right, not much time remaining. I just want to talk briefly about the future. Robotics is predicted by many people to be the next big business. Reports talk about tens of trillions of dollars of new business. Everyone's got enough computers, right? No one's got enough robots right now. So in 10 years' time, you're going to have a house full of robots, just like now you've got a house full of computers. So there's lots of applications for this robotic technology, clearly in manufacturing, smart co-workers. In the construction industry, again, smart co-workers to reduce the labor intensity of that particular industry. Infrastructure inspection, medicine that I've talked about, and also in agriculture. So, take-home messages. Robots are machines that move stuff from A to B. Computers just move information. Robots move real physical stuff. They can work 24/7. They don't look like what you might think. right? They don't look like R2-D2 or C-3PO. They look like anything. Their applications are unlimited. They're getting better and better very quickly, and in the future, we won't give them a second thought. And if you're interested in any of these topics, you want to read up on them, these are two quite good books, one by Martin Ford and the other by Brynjolfsson and McAfee. Give you a nice introduction to the potential of robotics to revolutionize industry and society. Thank you.